Okay, so let's begin with the quiz that we were handling. So in the quiz number 3, we had to solve second order differential equation with inhomogeneous term. So we did this question number 1, and we saw that the value that we got at the end for verification did not match the initial condition. And similarly, when we tried to do the question number 2, we ran into a similar thing, and the ultimate solution did not satisfy the initial condition. So basically, I opened this problem for all and asked you to come up with a solution, but I have not received any response in these 2 days. So I am now rectifying the problem and telling you the solution to the issue. When we did the same problem using Laplace transform that we are studying right now, we saw that we got to the same to the correct result, and it satisfied the initial condition. So obviously this answer has some problem with it. It must satisfy this initial condition. And from the Laplace transform solution, we see that while these values were the same, these coefficients were different. And in fact, because this term will zero out at t is equal to 0, so we must have such a value here that the difference of those values added with this 1.34 must be 0. So we have a problem here, and the way we did it suggests that the problem is with the homogeneous solution. So in the homogeneous solution, when we take the right hand side of the differential equation equal to 0 and we try to solve it and find these two coefficients, is where the problem must lie in both the questions, question number 1 and question number 2 as well. So let us take this question number 1 once again, and now I have basically revised my lectures and I have found where the issue was. So this is an errata. It is a correction that I want to make. So it is very necessary for every student to carefully look at it. Up till now, we have seen that in solving homogeneous second order equation with inhomogeneous term, second order differential equation with inhomogeneous term, we have been doing it this way. So in general, if this is a second order linear differential equation with constant coefficients with an inhomogeneous term on this side, how we have been solving up till now what I taught you earlier, which has a problem with it that needs to be rectified today. So let us revise what I have taught you till now, so that you can exactly pinpoint where the issue is and you can correct your learning from it. So the first step we would be doing is to solve or to find the homogeneous solution. So the homogeneous solution XHT would be found generally with two terms with two unknowns of this sort. So C1 e raised to power R1t, one of the values of R, if there are two distinct values, or if the two values are equal, then we have a term t here. And in finding the homogeneous solution, I told you to find this C1 and C2 based on the initial conditions that were given with this differential equation. So x at 0, or in general if we say x at t naught is equal to x naught, and x dot at t naught is equal to u naught, then using these initial conditions we find these coefficients c1 and c2. And then in the second step we find the particular solution. xpt, which based on the form of gt gets a form here. So if gt is an exponential function, this will be an exponential term here. If it is a trigonometric function, sine, cosine, we get a general solution which have a sine term and a cosine term with two coefficients that are unknown, and we use the equation to find those coefficients or constants. So basically xpt has a general form of this gt, and we saw that there are three cases. So if we have the inhomogeneous term is an exponential term or a trigonometric term, or it is a polynomial, then for an exponential term we say x particular solution is something of this sort. So c e raised to the power of the exact same form. If it is an exponential term, we say suppose it is c gt, where gt is exponential. And if it is a trigonometric inhomogeneous term gt, say sine or cosine or both sine and cosine, then xpt is equal to some constant a into sine term, whatever it is, sine of whatever is it in here, say it is sine t plus b cos of t. So if the inhomogeneous term is sine 2t, we get sine 2t and cos 2t here. And if it is a polynomial of degree, say of degree n, then we get the solution equal to some constant a n t power n plus a n minus 1 t power n minus 1, and so on till you get to a 0 t power 0. So a polynomial. And we say this is a solution to this differential equation, and then we put this assumed solution into this differential equation, and then using the coefficients of each term we find the values of these constants and find the solution. And then at the end we say, in the third step, we say the general solution or the overall solution xt would be equal to the homogeneous solution plus the particular solution. So that is what I taught you. And if you should note, the homogeneous solution depends on the initial condition, whereas the particular solution does not depend on the initial conditions. So let me say not initial conditions, but only depends on the forcing function or the inhomogeneous term. Forcing function or the inhomogeneous term. So this was what I taught you. It is more or less exactly what we should do. However, there is one very small point that has created all these mistakes, is that when you find the homogeneous solution, you actually do not find C1 and C2 here. This is important. This is that bit that I missed and so created all this problem. Do not find C1 and C2 here. We just see what is the form of homogeneous solution here at this point. Then we move to the particular solution. Then we say general solution would be equal to this thing. Now this thing, now when writing this, we are going to say, suppose the differential equation is, let me give you a general example. So if the differential equation is, say 2 e raised to the power minus 2t, or say minus, this is 3, so that we do not get too confusing 2's, and the initial conditions are, say, x of 0 is x naught and x dot of 0 is u naught. Then we say, when we have found the particular solution, suppose by solving this we found that the roots of the characteristic equation are real and distinct, then we say the homogeneous term would be C1 e raised to the power 1 value of r plus C2 e raised to the power the other value of r, say r1 and r2. So this is the form of the homogeneous solution. Plus, because it's exponential, we know we are going to get a term with a constant and exactly of the same form that is found here. So this is going to be the solution. And this A is the particular solution, and the particular solution is any solution of this differential equation. So if you just take this part and put it in here, we exactly know the value of A. So A would be known by the time we come here. But C1 and C2 are not known by the time we reach this step. So xt is equal to C1 unknown, e raised to power R1 known, t, plus C2 unknown, e raised to power R2 which is known, t, plus A which is known, e raised to power minus 2t. This will be the solution, final solution. And still you have to find C1 and C2 here. So now use initial conditions in finding values of C1 and C2. So that's the bit. So the important bit is, in the third step, when you write the general solution, you now find the constants in the homogeneous solution. Let me elaborate it once again, that do not find C1, C2 here, and when you are dealing with particular solution, find the constants by using the differential equation itself, not the initial conditions. So I hope you understood the mistake. So in this question, where lies the mistake? So if we have to redo it, let me take a red ballpoint and let us try to solve it over here. I hope we do not create too much dirt or okay, let's try to do it over here. This is question 1 of the quiz 3. The homogeneous term is of polynomial form. So what we have done correctly is finding the particular solution. This is correctly done. All A, B, C are correctly found. So this is it. However, so had this been a homogeneous second order differential equation, that is, we had 0 over here and these were the initial conditions, then the answer would be, the homogeneous solution would be 0. That's correct. All this is correctly done. But when the equation is not a homogeneous equation, has an inhomogeneous term, then these values of C1 and C2 are not correct. Instead, we should just be stopping here. So what we would be doing, we would stop here. That's it. So this part not to be done for inhomogeneous second order differential equation. Okay, so what we should instead do, when we reach this step, this will be the particular solution, and we will at this point say the general solution would be the particular solution plus the homogeneous solution. That would be e raised to the power minus 5 by 8 t c1 cos of square root 7 by 8 t plus c2 sine square root 7 by 8 t. It's not important that we take these fractions as 5 by 8, which you can replace them with the decimal values and this one as well. That's not the point. So if this is now the complete solution, it must satisfy the original differential equation. So now using the initial conditions, we can find what C1 and C2 is. So at t is equal to 0, what do we get? X of 0, which is 0. 0 is equal to 0, 0 plus 4.5. You see, we got this thing. When we applied t equal to 0, we got this thing. Obviously, this has to go in order for this to become 0. So this 4.25 was not present here, and that was creating all the trouble. So 0 minus 0 plus 4.25 plus, when we are putting t is equal to 0. So at t is equal to 0, cos of 0 is 1, e raised power 0 is 1. So we get c 1, and sine 0 is 0. So we got c1 is equal to minus 4.25. And now you can very easily see that with this value and this solution, when we put t is equal to 0, we are going to get 0, 0, 0 and 4.25 plus 1, 1 and this minus 4.25, which is 0. So I think this would be the solution, but let us try and find that C2 as well. So let us take the derivative, and then put t is equal to 0. So we get the derivative of x and then putting t is equal to 0 is 0. 0 is equal to the derivative of this thing, and then putting t is equal to 0, still will have t in here, so this will 0 out. The derivative of this is minus 2.5, and putting t is equal to 0 is not going to change this constant. So minus 2.5 plus the derivative of this thing will make it 0. And once again we come to this complicated term in the UE form. So if we take the derivative of this and keep this as is, we are going to get minus 5 by 8, and then putting t equal to 0 will make this exponential term 1, and then taking this as is, this will be, cos 0 is 1, we are going to get c1, and this term will 0 out. And in the next time, when we take this term as is, so we put t is equal to 0, we'll make this 1, and then take the derivative of this. The derivative of this will have sine, and sine 0 is 0, so we don't consider this. And the derivative of this would be, and sine of cos of 0 is 1, so we are going to get under root 7 by 8 c2. So what do we get here? We know c1, so 0 is minus 2.5 minus 5 by 8, c1 is minus 4.25 plus square root 7 by 8 c2. So c2 would be equal to Let me open the laptop because I don't have a calculator. And I need to use the system's calculator. So C2 would be equal to minus 2.5 minus 5 by 8. Rather, we should start with minus 5 by 8, which would actually become plus 5 by 8 into 4.25, positive value minus 2.5. So C2 would be equal to minus 0.15625 divided by under root 7 by 8, whatever this value would be. So let me copy this. So square root of 7 divided by 8 divided by the previous value, which obviously is the inverse of what we want. And this is equal to 0.473. So based on this, the ultimate solution that we get is, I'm writing the homogeneous term first, e raised to the power minus 5 by 8 is actually 0.625, t c1, which is minus 4.25 cos of what was square root of 7 divided by 8, 0.331 plus 0.331, sorry, cos of this thing, t plus C2 0.473 sine of 0.331 t plus 0.5 t square minus 2.5 t plus 4.25. So if we put t is equal to 0 now, we get 1 here. Cos of 0 is 1 minus 4.25, sine of 0 is 0. So minus 4.25 plus 0 minus 0 plus 4.25 is 0, which is the correct solution. And similarly, in this question number 2, obviously finding this C1 and C2 here is what is not required here. Instead, we will solve it till the end using C1 and C2 and then put it in the original differential equation and then find what is required. So we would have done till now. This is the form of the homogeneous solution. So we stop here, and then resume from here. So these steps are not to be done. So at the end, when we will come to this point, we will say this is the overall solution would be C1, this thing, and plus this coefficient would be, we will replace this with C1 and this one with C2 and everything else the same. And then we will put t is equal to 0 in that to find the values, find C1 and C2 here. So let us see what that would be. So IT at 0 is, what were the initial conditions? 0. So 0 is equal to C1 plus C2 minus sine 0 is 0, cos 0 is 1, plus 1.34 is one equation. And then when we take the derivative and then put t is equal to 0, we get an equation 20 is equal to, the derivative of this thing is going to give us minus 1.75 C1 minus 18.25 C2, and the derivative will be cos, and cos of 0 is 1, minus, so this 2 would be here as well, 2 into 0.94, and the derivative of cos is sine 0 is 0, so that will not play its role in here. So finding the values of C1 or C2 from here, so C1 is equal to minus C2 minus 1.34 is going to give us 20 is equal to minus 1.75 with C1 minus C2 minus 1.34 minus 18.25 C2 minus, we are going to get 1.88, and here we get 20 is equal to 1.75 minus 18.25 C2 minus 1.88 can come over here, and this minus 1.75 minus 1.34 can also come here, minus minus plus with the negative sign. So minus 1.75 into 1.34 minus 2.345 plus this thing 2.345. So we got 20 plus 1.88 minus 2.345, which is 19.535. We get minus 16.5 here divided by 16.5. So we get C2 is equal to minus 1.184, and C1 would be minus C2 minus 1.34. C1 is minus 1.34, which is minus 0.1561. So I hope these are the correct values. Let us see. So minus 0.15 C1 and minus 1.184 becomes minus 1.34 obviously, and plus 1.34 is going to give us 0. So the solution is, so the final solution is, I don't have space for that, but final solution would be IT is equal to minus 0.1561 e raised to the power minus 1.75 t minus 1.184 e raised to power minus 18.25 minus 0.94 sine 2t plus 1.34 cos 2t. This is the solution that satisfies the value at t is equal to 0 at least. I hope this was what was the solution that we did using the Laplace transform. So I hope you understood this. I missed on a simple point, and you see when we did the problem and we verified it was that when we understood that something is amiss and we went back, I went back and I revised, and then I found out what was the problem, and the learning I have obtained in doing this is immense, and therefore that is why a teacher emphasizes you to do some problems after understanding a concept. So when doing a problem you run into a mistake, that is when you actually learn something. So I have just flipped this to see the same problem done using the Laplace transform, and we have indeed more or less come to the same values. Obviously there are some rounding errors, so we have almost the same value. So we have 1.561, once rounded to probably this value. We have 1.184, this value. We have 1.34, 344, 0.94. So basically it is all matter of rounding. So this is more or less the same answer. That's a big relief, and I have no hesitation in accepting my mistake, because anyone can, as I often say, anyone can commit a mistake. The issue is not learning from one's mistakes. So this is more or less a recap of our in fact I have covered both the two types, the inhomogeneous term being a polynomial and the inhomogeneous term being a trigonometric function. So the third type you can cover yourself with the inhomogeneous term being an exponential, and try to do one or two problems yourself, and that's it. You are good to go for at least a second order differential equation. And please, whatever problems you do now, whether of first order differential equation or second order differential equation with a homogeneous term or with an inhomogeneous term, always do the same problem in both the domain, the time domain, the classical methods that is, and also in the frequency domain or the S domain, or the using the Laplace transform. So basically that is our course for the second sessional, and with this lecture I believe that we have covered the stuff that is needed for the sessional. Let me have a look at the videos that I have uploaded. I may cover a few other parts before we complete this week, and I will upload those videos maximum by tomorrow, so that you have ample time to understand them and review them. Once again, I will be posting a small problem on Friday, and you will have exactly 24 hours to do it and send it to me on the email designated for the course. And you will be considered present only if you have done the problem yourself and not cheated. By cheating, you are going to make yourself absent, and attendance is in a way necessary.